This slide shows the right-hand rule, and so if we're thinking about a cross product, we point our finger in our first finger in the direction of U, U cross W, and our middle finger in the direction of W, and our thumb represents U cross W. So if I had Z is equal to U cross W, then my thumb would represent Z. So in this example here, we're going to do this example in just a minute, but if I want to use the right-hand rule to determine the force, and the force is given by QV crossed with B, and that would give me my force. So I would point my finger in the direction of V for the particle, and I would then have my middle finger point in the direction of B, and I like to point all of my fingers in the direction of V, and then bend them into the direction of B. And then my thumb represents the direction of the force. So here, and also thinking about this, my QV cross B, each of these is 90 degrees to one another in this example here. So that I know that if V is perpendicular to B, then I know that F has to be perpendicular to V and B. So I know that I'm going to have my F in a different direction than either V or B, and that it has to be 90 degrees to both. What about if I wanted to do this mathematically? I can see what is the cross product if I want to think about a triangle. And so if I have two vectors U and W, in order to find the cross product U cross W, I want so here I have U, and now if I want to cross it with W, the part to cross means the part that's perpendicular to U. So I want to take the component of W that's perpendicular to U. And so I would have the perpendicular part, if this is theta, that's going to be sine. So sine is opposite over hypotenuse. So this is the part that I want, this W sine theta. So U crossed with W gives me U W sine theta. So it's U times the part that's perpendicular to U, which is W sine theta. I can also think about it the other way. I can say U sine theta times W. So in this case, I have W, and then this is my U sine theta. So this is the part that's perpendicular to W. So I can do it that way as well. When we're specifying 3 dimensions, out of the page is like an arrow. So if we think about it like an arrow, if I say that this is my x direction, so this is x, and this is y, then out of the page is z. So I can draw it like this, but sometimes it's nice to represent it just 2-dimensionally. So out of the page, if I think about an arrow, out of the page, this would be the tip of my arrow, and the tail of my arrow would be somewhere way back into the page, but the arrow would be pointing towards me out of the page. In this example, this vector would be into the page, so the tip would be way into the page, and I'm seeing the tail of the vector. So here I'm seeing the tip of the vector coming towards me, and here I'm seeing the tail of the vector going away from me. And that would be, so I would specify x would be to the right, y would be up, and this would be out of the page, and this would be into the page. So in this chapter, the way we're using the cross product is we're finding the force on a moving particle, say Q, and that equation is F is equal to QV cross B. And we also see F is equal, and this is a vector, F is also equal to Q times V over C crossed with B bar. And B bar is just another way to express the magnetic field, but it's in units of newtons per coulomb, which are the same units as the electric field. So that can be convenient. So if I wanted to think about this, the QV would be, if I'm thinking about the right-hand rule, the QV, I would point my fingers in the direction of V, and then I would bend my fingers in the direction of B, and my thumb would represent force. So for this first example, we're going to do some of these in class, but I wanted to do 1 or 2 so that you'd understand. My fingers would point out of the page towards me, and then my fingers, I'd bend them down, and so therefore my thumb would point this way. So that would be my force, except that they're talking about a negative charge. And so see Q, V cross B here, this would be for a positive charge. If Q is negative, then my force is going to be this way. So force for negative, and this would be force for positive. So let's do this one also. So if I point my fingers down, and then my fingers have to bend into the page, so then my force is this way, F positive, or for the negative charge it's going to be this way, F negative. And so you can continue on trying each one of these examples, and we'll do that in class. Now here's another way to think about it. This is an electron beam gun where the electrons are traveling down the length of the gun. And so what you're able to do is you bring a B field into the vicinity of this electron beam. Without the B field, the electrons just go right down the middle and they land at the middle of the screen. If you bring a B field near them, then you cause the electrons to bend. And so in this case, if I point my fingers in the direction along here, so towards that screen this way, and then I bend my fingers down in the direction of B, then my thumb points to the left. So that would be F positive. But since it's negative, my electron moves to the right. And I can see here, if this is the center, my electron has bent and moved to the right. So I can do the same here. If my electron is, I point my fingers in the direction that the electron travels this way, and I have to bend my fingers in B, then my force is going to be to the right for a positive charge. But since it's a negative charge, my force is going to be to the left. I have to multiply it times a negative. And so you can continue through those examples as well. So this is about Earth's magnetic field. So Earth has a magnetic field, and you can see that if this rotation axis here is given, and I can see that the magnetic field is at an angle. So the Earth's magnetic field is not aligned with its geographic center. So I have an angular difference between my magnetic pole, my magnetic axis, and my geographical axis here. And the other thing is that by convention we have determined that if our compass is pointing north, then that's toward the North Pole. But we know that if the needle of the compass is pointing one way, we know it must be pointing towards the South Pole. So actually there's a South Pole, there's actually a South Pole at the geographic North Pole of the Earth. And these field lines are fairly parallel to the Earth's surface as we get further away from the Earth here and out more towards the equator than at the poles.